This is Tony Roth, Chief Investment Officer of Wilmington Trust, and you're listening to Capital Considerations. We're back with Dr. Peter Menocal, the President and Director of the Woods Hole Oceanographic Institution, as I mentioned in the first episode, known as WHOI. And in the first episode, we really talked about the health of the oceans today, the fact that the oceans are heating, the fact that they are becoming increasingly polluted, that our fish stocks are being reduced. But at the same time, we concluded with some hope in the first episode around climate change specifically. Peter highlighted for us the very large proportional quantity of carbon that's stored in the world's oceans relative to the atmosphere, and hinted at the possibility that the oceans may be able to store additional carbon without having negative implications for the ocean, and that could potentially help to arrest or maybe even at some point reverse climate change, which is primarily caused by these greenhouse gases, carbon dioxide by far being the greatest contributor to global warming. Also, as with every episode, I want to remind everybody that Wilmington Trust is politically neutral and we take no side one way or the other on any of the issues that we are discussing from a political standpoint. So with that, Peter, Dr. Menocal, we're so happy to have you again for our second episode.
I'm happy to be here, Tony. Thanks for having me again.
I think the place to start, Peter, is to draw an important distinction, which is that on the one hand, we talked about the fact that the ocean has absorbed, let's call it 90% plus of the energy that's come into the planet and been trapped in the planet that has contributed to global warming. And if we didn't have the oceans to absorb that energy, the degree of global warming we'd have would be vastly greater because that energy would be stuck in the atmosphere instead of going into the oceans. That would make it appear as though there's sort of a zero-sum relationship between energy going into the oceans versus energy going into the atmosphere. Either way, you're going to end up with a warmer planet. It's actually more complicated than that because there's the notion of carbon. Carbon is not energy, carbon is matter. From a very layperson's perspective, and I'm sure I'm going to mess this up dramatically, is the idea somehow that energy can come into the planet and be converted to this inert, harmless carbon and sit in the ocean rather than warm up the atmosphere?
Let's start at the beginning, which is really, why is carbon dioxide a greenhouse gas? And it's a triatomic molecule, CO2, so a carbon and two oxygens. And the reason why it's trapping heat is that as the sun hits the Earth's surface, warms up the Earth's surface, and the Earth re-radiates what's called infrared radiation back out to space. This molecule, because of its size and its structure, actually vibrates in response to that infrared radiation and actually re-radiates that heat back to Earth's surface. And so the sort of simple way to think about it is that the more of this greenhouse gas that's in the atmosphere, the more the atmosphere traps heat and re-radiates that energy back to the Earth's surface.
Historically, most of that energy that's radiating back to the Earth's surface has been absorbed by the oceans, and only a relatively small proportion has resulted in the heating of the air around our planet, the atmosphere.
That's right. So over the last century and a half of the Industrial Revolution, as carbon dioxide is built up in the atmosphere has trapped more heat, re-radiated it back to the Earth's surface. Well, 3/4 of the Earth's surface is ocean, and the ocean is very well mixed. And so the ocean has taken up 90% or more of that excess heating. Interestingly, the ocean has also taken up about 1/3 of our carbon emission since the Industrial Revolution. So the ocean is actually this natural sponge for carbon dioxide. The ocean's ability to take up that carbon is something called the solubility pump, and it's just the fact that as you build up more carbon dioxide in the atmosphere, it pushes like a piston into the ocean. And so crashing waves and the bubbles that go into the ocean dissolve that carbon into the surface of the ocean, and the oceans take up about 1/3 of every pound of carbon we put into the atmosphere.
So two processes going on then. One process is really a heating of the atmosphere and the ocean through this energy that's reflected back towards Earth instead of going out into the solar system. And the second process is some of that carbon dioxide that is causing the energy to be reflected is, instead of staying in the atmosphere, is being converted to carbon sitting in the ocean in a fairly harmless
Mhm.
form.
An easy way to think about it is that the ocean is a two-time hero. It absorbs the vast majority of the excess heating that would otherwise be heating up the atmosphere. And it also absorbs carbon dioxide that actually reduces the amount of warming that we experience here on the planet. So were it not for the oceans, this is a very sobering result. The planet would be uninhabitable for humans.
So the carbon that ends up in the ocean, that's harmless.
Yeah, it's actually causing a lot of problems for the ocean. The ocean's uptake of that carbon is ocean acidification. This is happening throughout the world's oceans. As the ocean takes up this excess carbon, it forms a weak acid, but that acid is strong enough to make it so that it's difficult for shellfish to form, for corals to form. And so it's actually does have a deleterious effect to the world's oceans. And this is absolutely something we're very concerned about.
It's fascinating just how uninformed I am, because I thought that the acid issue in the oceans was that the poles were melting and all that fresh water was causing the oceans to become less acidic.
You're not the first person to make that association, but it's actually, I used to teach this when I was at Columbia. I would actually have a glass of water at my podium when I'd be in my lectures. There'd be various little instruments inside of this glass of water, and what it was secretly measuring was the pH, the acidity level in that water. And what would happen is in the course of my lecture, well, I've got, in some cases, 500 students in that lecture hall. They're all breathing. They're all oxidizing their breakfast.
Right.
They're in that room.
Excreting carbon dioxide.
Exactly. And so that's carbon dioxide is actually making its way into my glass of water, and it's making it more acidic. And so about halfway into the lecture, I would show them the decreasing pH, the increasing acidity of my little glass of water right in front of them. It's a bit of a small example of what's happening in the oceans.
Given that last conclusion, how could it be the premise of our episode is that somehow we can pull additional carbon dioxide out of the atmosphere through some process? In other words, we can speed up or assist the oceans in their natural ability or propensity to pull that carbon out of the atmosphere, which would then lessen the greenhouse effect, lessen global warming. But we would be doing it, would we not, at the expense of this problem in the oceans, the acidification? So why would we want to do that?
Herein lies the interesting observation, which is that carbon gets into the ocean in two ways. One is this solubility pump that we just talked about, which is the invasion of atmospheric carbon into the surface of the ocean. But the reason that the ocean has 50 times more carbon in it than the atmosphere, in other words, it's the largest exchangeable reservoir of carbon on the planet. The reason that exists is because the ocean is a living fluid. It has life and algae, and the growth of that organic material in the ocean acts as a carbon pump, a biologic pump that captures carbon from the surface, and then that dead material rains through the water column, passes through a zone. It's about a half a mile deep in the ocean called the twilight zone. This is a place where the carbon is metabolized by bacteria and turned into dissolved carbon. And so in the bottom of the ocean, or in the abyss of the ocean, the deep, dark, cold regions of the ocean, that is 70% of the planet, those regions of the oceans are just packed with dissolved carbon, and it represents something like 90% of the carbon storage in the ocean. And it gets there by virtue of this rain of organic material that makes its way into the deep sea. That carbon, when it gets to the bottom of the ocean, has what's called a residence time, the time it takes for that carbon to actually make its way back up to the atmosphere, of centuries to millennia. So in other words, this biologic pump is pumping carbon to the bottom of the ocean naturally, and it's stored there safely, naturally, for hundreds to, in some cases, thousands of years, for example, in the deep Pacific. So we're looking into, can that natural ability for the ocean to take up carbon and safely store it at depth, are there ways to enhance that process or even reverse the ocean acidification? And we can get into how the technology is behind that.
Yeah, so let's do that. I want to make sure that all of our listeners understand that there's a way to get that carbon dioxide, or that carbon that comes from the carbon dioxide, down to the bottom of the ocean without further acidifying the ocean?
The acidification is happening in the surface of the ocean because the atmospheric carbon is dissolving the surface of the ocean, making a weak acid. In the case of the biologic pump, organic organisms, so algae and fish and the like, are taking up that carbon and turning it into organic tissues. That forms the base of the food chain in the sunlit portions of the ocean. And then fish, just like people, they pass on, and that material rains through the water column very slowly. In fact, if you go down to this depth, about a half a mile into the ocean, it's what we call the twilight zone. If you were to flick on the lights, it would be like a snowstorm. So as that carbon makes its way into the deep ocean, it gets further degraded by bacteria, and it turns back to dissolved carbon in the deep ocean. That is the way in which the oceans are just packed with carbon. That's the process by which the ocean has this excess of carbon, 50 times more than the atmosphere.
So analytically, in order for this to work, and I think it's called carbon dioxide removal.
That's correct. Yep.
CDR.
CDR.
It seems like we need to solve for two problems. One is we need to enhance the ocean's ability to essentially absorb that carbon before it acidifies the ocean and turn it into a biologic. And then the second is we need to go back to the first process, which is the ocean as a heat pump just absorbing carbon dioxide. If we can solve the second thing, which is to say that we can get that carbon to the bottom of the ocean without having the acidification, how can we get the ocean to absorb even more carbon dioxide? Do I have that right?
The easiest way to think about this is, why do we need carbon dioxide removal in the first place? For example, we can grow trees on the land surface, and that can be used to take carbon out of the atmosphere. There's another process called direct air capture, and there's a plant in Iceland that was recently developed by a company called Climeworks. Well, those processes are actually harder to do and harder to scale than people would imagine. That
Right.
plant in Iceland, for example, that takes up carbon dioxide direct air capture, it takes up about 3 seconds of annual emissions per year. So you need a whole bunch of those factories to take up the carbon at the scale at which we emit it. So the number one takeaway from this is that we have to reduce emissions first and foremost. That's the number one place to start. But we're not doing it fast enough, and so hence this idea of carbon dioxide removal. How can we take it out? So then there's this idea, well, let's grow 100 million trees and afforest big parts of the world's surface. Well, 100 million trees represents about a half an hour of global emissions. Fast forward to the ocean, this uptake of carbon by the ocean and the surface, the ocean naturally takes up about 3 months of carbon emissions per year. So then the question then becomes, are there processes by which the ocean could naturally take up additional carbon and store it in the ocean in different parts of the ocean? A National Academy study was convened about a year ago, looked at the 3 leading ideas, and I can briefly review those. One is,
Yes, please.
Growing kelp, so intentional fields of kelp, if you will, in the ocean. They grow, they're bundled, and they can be sunk down to the bottom of the ocean where they can reside, and they degrade very, very slowly. And remember, carbon is down there, is securely stored at the bottom of the ocean, let's say 3 or 4 miles deep in the ocean, for centuries to millennia. So it basically buys you that much time.
So if the kelp is in the bottom of the ocean, how could it cause the surface of the ocean as that absorption pump to absorb more carbon dioxide?
By actually deliberately growing fields of kelp, if you will, that's organic matter. If you take that organic matter that's captured the carbon from the surface ocean and then physically move it to the bottom of the ocean, to the abyss, you're literally taking that mass of carbon out of the atmosphere, because that carbon originally came from the atmosphere.
So you'd start by putting the kelp on the surface. It would absorb the carbon dioxide, and then you would move the kelp to the bottom of the ocean before it could actually acidify the ocean. So you'd be solving 2 problems at once. You'd be capturing the carbon, you'd be increasing the ability of the ocean to capture carbon, and you'd be doing it in a way that does not acidify the ocean.
Right. It actually would counteract the ocean acidification. Now, before we get into any other ideas, I just want to make sure your listeners understand that I'm not advocating for this. And in fact, there are companies that are already doing this. My concern as the head of the Woods Hole Oceanographic is that we need to have sort of a carbon cop. We need to have an organization that's paying attention not only to the viability of these technologies, but also whether they're net positive or net negative to the ocean. What are the unintended consequences? And this is why we need an independent research organization to observe and monitor this process.
So it could be that one day you would advocate for it, but you're not there yet, is what you're saying.
All of these technologies that I'm about to mention to you, all of them have been demonstrated to work not only on a benchtop, but also in what we call a mesocosm. That is a small, restricted part of the ocean where it's been tried.
And with respect to the first technology, which is seeding the surface of the ocean with kelp and then sinking it essentially, and I'm sure I'm being overly reductionist and
No,
crude.
that's good enough.
Okay. So that first technology, if you were to conclude that the net impact on the ocean was in fact not negative, and obviously the net impact on the atmosphere is very positive, how scalable do you think that might be?
This ability to grow kelp at scale, we're talking a really massive scale. I mean, 1 billion tons of anything is a lot. Growing kelp at that scale has never been done. But just to give you an idea, if you were to build a kelp growing facility around the United States, occupying the full EEZ of the United States, exclusive economic zone, that would represent about 1 billion tons, 1 gigaton of carbon per year. And that's obviously not something we're going to do, nor something we should do, but it gives you an idea of the scale of the challenge.
Why couldn't we just grow enough kelp out there so that it would just multiply, sort of like a horror movie, but it would be a positive weed, and then it would help the atmosphere?
Imagine that this is done and the weed is actually not beneficial, that it's actually a net negative. And first of all, you have to document that, but then you have to make sure that that technology is not pursued. And that's
Right.
really the role of an independent oceanographic institution, is to make those observations, to do that monitoring, to be the arbiter, if you will, to be the observer of these really sort of large experiments that are being considered. And I just want to start out by saying, the reason that we're even considering carbon dioxide removal, whether it be terrestrial or marine, is because we have so delayed action on reducing carbon emissions that now carbon dioxide is required to stay under this threshold of warming that we're desperately trying to avoid. One of the reasons that so much attention is focusing on this is just the sheer urgency of the need.
We've talked about kelp. What's number two?
The second is one that's maybe a little bit harder to describe, but indeed works very well, which is called alkalinity enhancement or alkalinity management. Mm-hmm. And the oceans are, of course, salty. And it's actually by virtue of that salt that the ocean actually can take up carbon and store it at the sheer magnitude that it does. It's attributable to a process called alkalinity, which is the opposite, if you will, of acidity. And the oceans are naturally alkaline. The pH of the ocean water is about 8.1 on the pH scale. 7 is neutral. So because the oceans are slightly alkaline, that makes the oceans a net sponge for carbon, just from the pure physics and chemistry of the ocean. So the idea of alkalinity enhancement is, as you can imagine, increasing the alkalinity of the surface of the ocean. That actually offsets the acidity of the ocean and makes the ocean a chemical sponge for carbon dioxide.
So basically, I go out, I buy some baking soda, and next time I go to vacation on the Caribbean and I go snorkeling, I just sprinkle my box of baking soda. I've done my good deed.
Sort of, but yes, that's correct. I mean, that's certainly in principle the idea behind it. So it's basically like a Tums or an antacid for the oceans. The interesting, even fascinating thing is that it works. Some recent experiments have been conducted in the open ocean, and there's actually a co-benefit, which is that as the oceans have become more acidic, the shell fisheries have suffered because they're basically having to build their shells in a more acidic ocean. Well, alkalinity enhancement actually makes the oceans more alkaline, makes shellfish grow stronger and more robust shells. And so it actually supports shell fisheries and corals.
So what's the scalability and cost, and what's the externality of that process? You have to put some energy into doing this, which itself is going to create emissions. How would you summarize for us the prospect of this particular avenue?
So, Tony, what we know is that the chemistry of this is very robust and very well known. What we don't know are the unintended consequences and the scalability. What we are doing actually right at this moment, we were just actually recently funded through an international competition to actually try this at scale in the northwestern Atlantic Ocean. The idea here is to not only track the efficiency at which this process can work and how quickly it can be scaled, but also to monitor the unintended consequences, the impacts on other aspects of the ecosystems to make sure that there are no adverse impacts. That's actually happening right now. And this is just one of several smaller, not at full scale experiments to assess the viability of the process, but also the efficiency and also the impacts on ecosystems.
It's easy to understand how all that kelp could be deleterious for marine life and objectionable for folks that might live on the coast and such.
Mm-hmm.
Again, as a totally uninformed layperson, the alkalinity idea seems to be inherently perhaps less damaging. If it turns out that it doesn't have a net effect on the ocean, without getting into the technicalities of it, is there reason to believe that it could potentially be done at a scale where the net impact on the climate is going to be positive when you consider the externalities that go into actually doing this type of thing?
So when we've done those kinds of economic analyses, the number is beginning to approach something like $100 a ton or less. And that's the current strike price for carbon on the global exchange right now, or actually on the European exchange. Another factoid that's interesting for people who haven't heard it is that we currently emit about 37 billion tons of carbon dioxide into the atmosphere every year from human activities. And if you just do the math and say, okay, at $100 a ton, which is the current strike price on the European market, that's a $3 to $4 trillion per year under-realized economy. It's a massive economy. And the current value of the global carbon market is something like 0.8 trillion or 800 billion. This is a market that is obviously emerging, it's expanding, but it's nowhere near realized. And so this is the concern, is that with such a big economic driver, there's going to be a need or a call to enhance these technologies. And so that's all the more reason why we have to lead the research and the technology to understand whether this is a good or a bad idea. Again, the smartest thing for us to do is just not put the carbon there in the first place.
Of course. So let's look real quickly at the third potential that you've decided to highlight for us today.
The third technology or approach that's being considered, and again, this is coming from a National Academy study that was conducted last year. In fact, one of our scientists participated in it. And actually, he's someone who's leading the research internationally on this third technology, which is called ocean iron fertilization. And it is not dumping iron filings into the ocean, as sometimes people think. It's using a soluble form of iron. Iron actually acts as what's called a micronutrient. The iron actually serves to help organisms build proteins for their structures. And there are vast regions of the ocean that are what we call high nutrient, low chlorophyll oceans. These are places where there's tons of nutrients, but not that much life in the ocean. And what was discovered about 20 or 30 years ago is that the one limiting factor to the productivity, the vitality of those parts of the oceans is iron. It's missing iron. And so if you go into those portions of the ocean and distribute in a very dilute way dissolved iron, which is really just like an iron oxide that's in the ocean, iron sulfate actually, it causes these blooms of algae and organic matter, greatly increasing the productivity of huge swaths of the ocean. You can literally write your name in the ocean with a stream of dissolved iron and leave this green trail of circles and lines in the ocean. And we've known this now for decades. The ocean iron fertilization idea or hypothesis is that if you do this at scale, it'll stimulate greater productivity in the ocean, and that enhances this rain of organic matter to the deep reaches of the ocean, where it can be stored for centuries to millennia.
Well, it's interesting because as you talk about these possibilities and we think about how complicated the ecosystem is, I can't help but recall what we're dealing with today in our financial economy. When we think about the unintended impacts of increasing interest rates on financial stability and the banks, that as obvious as it may seem now, that the increase in rates had on our financial stability and causing bank failures. And I would have to believe that by comparison, that's a fairly simplistic closed ecosystem compared to the oceans. And so as exciting as these possibilities are, it's sort of scary that we even have to be thinking about injecting or introducing massive amounts of iron to change the productivity of the oceans, or to be changing the basic chemistry of the ocean through alkalinity strategies.
The fact that we're having to explore these really large scale, planetary scale fixes to a problem that we've caused is truly daunting. And this is actually all the more reason why we have to bring the best minds to bear on whether and how to do this. The best thing that we can learn is that we understand how the ocean functions, the services that it provides to humanity, and we're there to protect it. The worst thing that can happen is that this is treated as an economic problem that has to be solved, and science is sidelined and not focusing on the monitoring and the verification of these actions on the essential functions that the oceans play to sustain humanity and, frankly, life on Earth.
You quantified the alkalinity idea for $100 per ton. Are we far enough along on the iron idea that we have a number on that?
It's around the same number. What's interesting and attractive actually about the iron fertilization hypothesis is that for 1 unit of iron that's added to the surface of the ocean to stimulate this excess productivity, it actually stimulates between 1,000 and 10,000 times more carbon uptake than the unit of iron that's introduced to the ocean. And this is because it acts as this micronutrient in the ocean. So you get a tremendous bang for the buck, if you will, for a small amount of iron. In fact, actually, to take up 1 billion tons of carbon dioxide would require something like 0.1% of the global iron production. These are huge planetary scale questions, and they require an observation capacity for the ocean that we do not yet have. And this is actually a focus for the Woods Hole Oceanographic. We are building something called the Ocean Vital Signs Network, which is to monitor ocean vital signs, but at a scale and a time resolution that's unheard of, that's never been done in the history of oceanography. And this is because the oceans are changing so rapidly and changing so profoundly. And the impacts of those changes are so existential to life on Earth and humans that we need to have those eyes on the ocean.
How do you think about the remit of the institution, of the Woods Hole Oceanographic Institution, WHOI, in today's world, and how has it changed to meet the exigencies that we're confronting today?
The Woods Hole Oceanographic, and remember, we've got 1,100 people here, scientists and engineers and marine operations, and it's just an incredible ecosystem of exceptionally dedicated and brilliant people. And throughout its 90-year history, it has always focused on addressing these basic science questions that inform how the ocean works. The ocean's a really big, complex, hard to study place. That was true, is true, and I think will forever be true. That said, we are now, this current generation and into future generations, we are living on a planet in transition. The ocean is changing in ways that are alien to any prior generation of humanity. It's our obligation to understand how those changes are occurring, how they impact people, and what they mean for future generations. And so a big part of what we're doing now at the Oceanographic is really stepping up to the plate and saying, how can our minds, our talent, our ships, our resources be applied to these really vexing, big, massive planetary scale questions. And there are very few places in the world where you have the luxury of pursuing these kinds of questions, and we do it gladly.
And I imagine that if anybody wants to be involved, the easiest thing to do is to jump on your website. Lots of ways to get involved.
Yep. And Tony, I just want to thank you for the invitation to join you on these 2 episodes and for your years of dedication to the Woods Hole Oceanographic.
Well, thank you so much for being here. It's really our privilege to have you, Peter. I want to thank our listeners, and I want to remind everybody you can go to wilmingtontrust.com for a full roundup of all of our latest investment and planning ideas.
This podcast is for educational purposes only and is not intended as an offer or solicitation for the sale of any financial product or service or recommendation or determination that any investment strategy is suitable for a specific investor. Investors should seek financial advice regarding the suitability of any investment strategy based on the investor's objectives, financial situation, and particular needs. The information on Wilmington Trust's capital considerations with Tony Roth has been obtained from sources believed to be reliable, but its accuracy and completeness are not guaranteed. The opinions, estimates, and projections constitute the judgment of Wilmington Trust as of the date of this podcast and are subject to change without notice. The opinions of any guest on the Capital Considerations podcast who are not employed by Wilmington Trust or M&T Bank are their own and do not necessarily represent those of M&T Bank Corporate or any of its affiliates. Wilmington Trust is not authorized to and does not provide legal or tax advice. Our advice and recommendations provided to you is illustrative only and subject to the opinions and advice of your own attorney, tax advisor, or other professional advisor. Diversification does not ensure a profit or guarantee against a loss. There is no assurance that any investment strategy will be successful. Past performance cannot guarantee future results. Investing involves a risk, and you may incur a profit or a loss. Any reference to company names mentioned in the podcast should not be construed as investment advice or investment recommendations of those companies. Third-party trademarks and brands are the property of their respective owners. Third parties referenced herein are independent companies and are not affiliated with M&T Bank or Wilmington Trust. Listing them does not suggest a recommendation or endorsement by Wilmington Trust. Private market investments are only available to investors that meet the U.S. Securities and Exchange Commission's definition of qualified purchaser and accredited investor. Facts and views presented in this report have not been reviewed by and may not reflect information known to professionals in other business areas of Wilmington Trust or M&T Bank and may provide or seek to provide financial services to entities referred to in this report. M&T Bank and Wilmington Trust have established information barriers between their various business groups. As a result, M&T Bank and Wilmington Trust do not disclose certain client relationships or compensation received from such entities in their reports. Investment products are not insured by the FDIC or any other governmental agency, are not deposits of or other obligations of or guaranteed by Wilmington Trust, M&T Bank, or any other bank or entity, and are subject to risks including a possible loss of the principal amount invested. Wilmington Trust is a registered service mark used in connection with various fiduciary and non-fiduciary services offered by certain subsidiaries of M&T Bank Corporation, including, but not limited to, Manufacturers and Traders Trust Company, M&T Bank, Wilmington Trust Company, WTC, operating in Delaware only, Wilmington Trust NA, WTNA, Wilmington Trust Investment Advisors, Inc., WTIA, Wilmington Funds Management Corporation, WFMC, and Wilmington Trust Investment Management, LLC, WTIM. Such services include trustee, custodial, agency, investment management, and other services. International corporate and institutional services are offered through M&T Bank Corporation's international subsidiaries. Loans, credit cards, retail and business deposits, and other businesses and personal banking services and products are offered by M&T Bank, member FDIC. Copyright 2023 M&T Bank and its affiliates and subsidiaries. All rights reserved.